lot of these are from the textbook, like the recommended textbook problems on chapter 9. Some odd and even ones. But the first question is, how can you tell a solution from a colloid? What's the difference? That was one of the first things we defined in chapter 9. We said a solution is a homogeneous or a heterogeneous mixture. Do you remember? It's a homogeneous mixture. And what's the difference specifically between a solution and a colloid? We said an example of a colloid is like milk. And we said a solution would be like salt water or alcohol or I think one thing. So this was one of the first slides. It's not going to go as fast as I want. Here was the table that differentiates these things. Okay. So colloids have bigger particles. They have like a lot of times biological molecules, things that are bigger. Solutions, the particles are very, very small. You can't filter them out. And that solution is usually transparent. You can see through it. Okay. That was kind of where we started with solutions, was identifying what exactly it is specifically. And so that's kind of my answer. Okay. Here, what would you guys say? How would you put it in your own words? Yeah, so the easiest answer is particle size. What's dissolved in the solution, okay? That's the main difference. So solution have smaller particles or solutes dissolved in them than colloids. Colloids, the solutes that's dissolved are bigger. That makes sense? Okay. Next, so we talked about principles and rules of solubility, like dissolves like. So that's what this question kind of gets at. Based on the predominant intermolecular forces, which is lone pairs of liquids are likely to be miscible. So you definitely had a question like this on your homework, I know. I don't even know, it might have been the same exact one. You guys remember? So what do we need to be thinking about when we answer this? Yeah, I mean, you just identify each of these liquids if they're polar, non-polar, ionic. So H2SO4. We should immediately recognize that as it's hydrogen sulfate. Is it ionic, polar, or non-polar? Yeah, that's a scream ionic to you because sulfate is a polyatomic ion. Okay. So H2SO4 is ionic.
To go about this, to determine like if they're likely to we should start by figuring out which ones are ionic, polar, or non-polar.
Yeah, you're just going to look at each molecule and identify what kind of molecule it is. If they're the same, then they'll be miscible. If they're different, then they won't be, except for the fact that polar and ionic things are miscible. Okay, does that make sense?
You said polar and ionic?
Yeah, are miscible. So what about water? So are these miscible or no? Yeah, check mark. Yes. Okay, you have octane and you have hexane. No, that's not hexane. That's a C6H6. Is that benzene? You don't have to know the names of it. I do. I like to know the names of them. What do y'all think about these? Yep, both
nonpolar. And how do you know? I mean, we're not drawing the Lewis structure out here. It's any molecules that are just carbohydrates, carbon, hydrogen only, are going to be nonpolar because all that's involved there are carbon-carbon bonds, which are nonpolar. The electronegativity difference there is 0. Carbon-hydrogen bonds, and the electronegativity difference of those bonds is 0.4. So nonpolar bonds all around. So both nonpolar, so yes, these will also be miscible. Okay, CH2, Cl2, and water. What do y'all think there? Yep, we already said that. That one's polar. Okay, it's also got Cl in it. This one I would like to draw the Lewis structure out. And remember, we actually drew this one out in lecture. I said there's 2 ways you can draw it. I said you could draw it like this, with the hydrogens like this, the chlorines like this, but you can also draw it like this, with the chlorine on either side, or you could draw them up and down, and the hydrogens on either side. And what you find out if you go look at electronegativity chart, which you will have on your exam 4 as a resource, that these bonds are polar. Okay, or you could draw them, you know, the dipoles in there. So what do y'all think? Yes, what? Immiscible? So you're saying that,
Because if that's polar. If it's in opposite directions, so they're non-polar.
okay,
It's symmetrical.
right, look, this is symmetrical. So these dipoles cancel. Now, the way I've drawn it on the left here, that doesn't look symmetrical, right? But what I said in class, I said, remember, molecules rotate, bonds are flexible, and these two are actually synonymous with each other. Okay, it depends on which angle. We're only being able to draw it in 2D on the paper, but they're 3D molecules. So if you can draw the molecule in such a way that it is symmetrical, that is a nonpolar molecule. Okay, even though you can draw it another way, doesn't make it polar. Okay, it's just a matter that we're not, we could rotate this, and it's hard to explain looking at it 2D. It really is. It's probably a very insufficient explanation.
So it makes it non-polar.
But it is nonpolar overall because those dipoles cancel, and it helps us to view that if we draw it as we draw it on the right there. So this is nonpolar. So now what do you think? So, and C is not miscible. Okay, CS2, CCl4. Yep. I'm pretty sure on electronegativity chart that carbon and sulfur have the same electronegativity. But again, you could always double check that on the exam. So this one's nonpolar. And it's a linear molecule. Looks like that.
So if C has 4 Cl's coming from it,
Mm-hmm.
it would also be non-polar solvent.
Yeah, it would look like this. We just erase those hydrogens. Cl, Cl, and then the up and the down dipoles cancel, and the left and the right also cancel. So this one's nonpolar too. So yep, A, B, and D would all be miscible. Okay. That's as complicated as solubility would get on the exam. Besides the fact that we talked about you can manipulate solubility. Do you guys remember what we said? When you have a solid dissolved in a liquid versus a gas dissolved in a liquid? We said you can manipulate their solubility with temperature. Remember how that works? So let's talk about a solid dissolved in a liquid. I guess I need a blank space. I'll go up to the title slide. So when you have a solid in a liquid, so you can think about it like sucrose in water, glucose in water, or sodium chloride in water. A solid dissolved in a liquid. How does the solubility change with temperature? How does the solubility change with temperature? If I decrease temperature, what happens to the solubility of that thing? Decrease the solubility. If I increase temperature, increase the solubility. The example I gave was with honey. honey's a super saturated solution. It's oversaturated with sugar. And sometimes when you have a very little honey left in the bottle, it like crystallizes. And you can make that sucrose go, or that sugar go back into a liquid form if you just heat it up. Okay, it kind of redissolves, right?
So if we increase temperature, it increases solubility.
There you go. If you increase temp, you increase solubility. Okay, what about a gas dissolved in a liquid? The example I gave, I remember the example I gave?
The drink part of it,
Carbonated drinks, a Coke, club soda,
if it any temperature increase,
my favorite, right, Carter? He hates them. Yep, if we increase temp, it decreases solubility. Okay. So we talked about that as well. All right, what do we have next? Okay, this is problem 9.38 from the textbook. Solubility of NH3 gas in water at an NH3 pressure of 760 millimeters mercury, 25 degrees Celsius, is 51.8 grams per 100 milliliter. And whoa, 27.0 grams per 100 milliliter at 50 degrees Celsius. So it's giving you two different solubilities because it's giving you two different temperatures. So we'll just work with one of these. I'll just forget that one. But you can see if you increase the temperature, this is a gas in water, it decreases solubility. You notice that? So which is what we just talked about. Okay. But for time's sake, let's just work with one of these. Okay. What is the solubility of NH3 if its partial pressure is reduced to 225 millimeters mercury? So what kind of problem is this? How would we work this? Henry's law. Henry's law. Which is what? Which is a law. Sorry, I accidentally bumped the screen. C1 over, that's right, C1 over P1 equals C2 over P2. So it says, what is the solubility? So it gives you a pressure, that's P1, and it gives you a solubility, that's C1, and then it says, what is the solubility? So we're looking for C2, and it gives us P2. Now, what are the things we got to check for before we just plug everything in? Make sure the units on pressure are the same, and they are, okay? So now we just say, okay, I'm gonna cross multiply both sides by P2. Cancels there, so we got P2 times C1 over P1. That's gonna be our equation to solve for C2. So P2 is the 225 times C1, which is the 51.8, grams per 100. And remember, you don't divide by that 100. You should treat it as a unit. Divided by P1, which is the 760 millimeters mercury. Okay. We do 225 times the 58.1. Leave that 100 alone. Divided by 760. You got it, Gracie? 15.3. We'll leave it at that since our first solubility only had 1 decimal grams per 100 milliliter. And so if pressure decreased, we noticed that solubility decreased, right? Because that's the way Henry's law says. If you increase pressure, you increase solubility of a gas in a liquid. If you decrease pressure, you decrease solubility of the gas in the liquid. Good morning. All right. Any questions on Henry's law? So remember, if you're solving for a pressure here, like if you're solving for P1 or P2, You just flip the whole equation upside down if you want, and then isolate that term, okay?
On the exam, do we have to show us against like multiple process line each day or whenever?
The answer is it kind of depends. If it's an open response question, I want to see all your work. And I forgot on exam 3, but I usually say, show all your work, right? If it's a multiple choice question, to be honest, I'm just flying through looking at the letters.
And then 760.
Like even if you showed all your work, but you still put the wrong answer, I'm gonna go with what answer you put on multiple choice. Okay.
That's 1 ATM, right?
760 millimeters mercury is 1 ATM.
And 225, that was like when would we have to convert?
Like if I said here, pressure was 1 ATM and then your second pressure was 225 millimeters mercury. Well, you would need to get them both in ATM or both in millimeters mercury. Whatever way you want to do it. It doesn't matter if you put in millimeters mercury, it doesn't matter. Now with the ideal gas law back on chapter 3, it did matter. Everything had to be an ATM, but with Henry's law, with the Boyle's law and the Charles law stuff, like the combined gas law, it doesn't matter as long as both the units are the same. Yeah, the only one it matters what the unit is the ideal gas law, which you won't have an ideal gas law problem on exam 4. Okay, you remember I was talking about this problem in lecture? I was like, there's a really good problem about Listerine. We're gonna do it now. If I like it so much, I don't know why I don't just save it for exams.
You put this on.
I knew that was coming. I knew it. A 750 milliliter bottle of Listerine is a 21% V/V, volume per volume, ethyl alcohol. Okay, why is it V/V and not W/V, which is a weight per volume? Dissolved in a liquid. A liquid dissolved in another liquid. So here the solution has a liquid solute, which is the alcohol. It's an ingredient in Listerine. Does that make sense? Listerine is the solution of all the things together. And ethyl alcohol is just one of those ingredients that's the solute we're focusing on, okay? So it's 21% ethyl alcohol. That's a high alcohol content. What is the volume in milliliters of ethyl alcohol in the bottle? So ethyl alcohol, again, it's the solute. Listerine is the solution. So how do we do this? How do we do part A? Let's write the equation that we need. That would probably be the best place to start. So I'm going to say percent of its volume per volume, milliliter per milliliter, is going to be equal to what?
Are we gonna do like 750 over?
So 750 is the Listerine. This is the solution.
Yeah.
And then this is the solute. So it should be, since we're dealing with two liquids here, what is our equation for our normal, like mass volume percent, weight volume percent? That's molarity. That's the other one. That's the other very important one. We'll do that in a minute. It's grams of solute over milliliters of solution times 100. And that's when you have a solid dissolved in a liquid, right? Because solids we would measure with units of grams. Here we have a liquid dissolved in a liquid. So how would we modify that equation? What do we measure liquids in? Units of? Yeah.
It'd be like 0.0575.
Not yet. I'm just trying to write the equation first. That's okay. So we're just going to modify it. We're going to say milliliters of solute over milliliters of solution. Well, that doesn't look like an M. Milliliters of solution times 100. You see how we changed the equation? Our other equation, the weight volume percent, looks like this. Grams of solute per milliliter of solution times 100. You see the difference? The top one we use when we have a liquid dissolved in a liquid, which is what Listerine has here. The bottom one is when we'd have like sodium chloride dissolved in a liquid. A solid dissolved in a liquid. Does that make sense? What we're doing? You see the subtle difference? Okay. So what are we trying to solve for? It says, what is the volume of ethyl alcohol, which is our solute? So which part of this equation are we trying to solve for? Milliliters of solute, which is this part right here. That's the part we're trying to solve for. So what are the other pieces and where do we plug them in? Because I can't solve for this unless I have the two other pieces, which is the percent and the milliliters of solution.
So we just have like blank over 750 something.
So we're looking for X there, our milliliters of solution, divided by our solution is the 750 milliliters of Listerine times 100 equals what? Yeah, it's the only percent we're given, right? That's the percent, so 21%. Okay, now are we good to go?
Yes.
Okay. So what do we need to do? How do you solve for X? Okay, like that. Cancels out over here. We have 0.21, whoops, equals X over 750. Then what? And remember, because this right here, that percent is a milliliter, it's a volume per volume, which means milliliter per milliliter. Okay, so again, we don't write those out when we write the percent, but if you know that it's said it's a volume per volume, the milliliters with the 750 end up canceling with the milliliters on the bottom up there. And so we'll just have 750 times 0.21 is what? 157.5, and the units there would be milliliters. That's how many milliliters of ethyl alcohol are in the, okay, so this is the milliliters of ethyl are in Listerine, okay? So don't drink Listerine. Is the moral of the story. Look. Has anybody actually ever seen it's a children's movie, but Paddington, the bear, have you heard of that movie? There's a scene in it where he downs some mouthwash. Okay, B. So this is the challenging part of this problem, I think. If the density of ethyl alcohol is 0.789 gram per milliliter, and the molar mass is 46.07 gram per mole, calculate the molarity of ethyl alcohol in the Listerine. What do we do here? And if you have access to the textbook, you can just write down what number this is. So it wants us to calculate the molarity. So what is molarity? Olivia, you said this earlier.
Yeah, moles over.
Right, so molarity is moles, and this will be of ethyl alcohol over liters of the solution, which is, what's the solution? Okay. Do we have either of these pieces? Okay, what do we have? Okay. And we don't have moles of ethyl alcohol. All we did so far is solve for the milliliters of ethyl alcohol.
So can we solve for moles by doing grams to moles?
Yep, yep. We can. But I want you to recognize you already have part of what you need. We're told we have 750 milliliters of Listerine. And in the problem to solve for molarity, we're going to divide by liters of Listerine. Just convert milliliters to liters, and that's the bottom part. Okay, all we're trying to do now is solve for moles of ethyl alcohol. So 750 milliliters equals 0.750 liters of Listerine. So we'll plug that in on the bottom in just a minute. Now, how would we get moles? Right now, all we have is this part down here. We know we have 157.5 milliliters of ethyl alcohol. Olivia's right. If we had grams of ethyl alcohol, we could just use the molar mass right up here, the 46.07, convert right to moles. We have, there you go. That's why they give you the density. You use the density as a conversion factor. You take the milliliters, the 157.5, convert from milliliters to grams using density. You see how the density tells you it's 0.789 grams for every 1 milliliter of ethyl alcohol? So you'll cancel milliliters, convert to grams. Okay. And then you take the molar mass, cancel grams, convert to moles. So 2 steps here to get moles, which is why this problem is challenging. So we'll start with the volume, 157.5 milliliters, and I'm going to abbreviate ethyl alcohol as EA. Okay, then we're going to take the density and we're going to plug it in. We want milliliters to cancel, okay? So that's this up here. So it should be 0.789 grams of ethyl alcohol on the top, 1 milliliter on the bottom. That's the density. And now you see how milliliters are going to cancel? So that gets us to grams of ethyl alcohol. Then what do? Plug in the molar mass. I'm going to divide by the 46.07 grams for every 1 mole. So we'll do 157.5 times the 0.789 divide by 46.07. We'll get the number of moles. Okay. Moles of ethyl alcohol. And now we'll plug that on top, divide that by the 0.75 liters of Listerine, and molarity will be 2.7 moles of ethyl alcohol divided by 0.75 liters of Listerine. I guess I just think this is such a great problem because it combines so many things that we have learned and are useful tools in this course. Density is a big one. Molar mass is a big one. And now concentration is a big one. We're using percent and molarity all in one problem. Okay. So, I mean, would you freak out if now that you've seen it, you're probably, no, that's easy, but. Reverse psychology, huh? Okay. Anyways, I don't want everyone to fail, so. What is the mass volume percent concentration of the following solutions? This is more concentration problems, but it's kind of more the straightforward kind. So A here, 0. I'll try to zoom in. 0.078 mole KCl in 75 milliliter solution. What do we need to do? What's the equation for mass volume percent? Yep. Grams solute, which is our what? What's our solute here? KCl. So we don't have grams of KCl. What do we need to do? So we need, what do we need to do? How do we need to solve for this?
Do we do moles to grams?
Mm-hmm. And plug it in. That's it. So molar mass of KCl. I can, wow, I can't read the 39. Is that what it says? Potassium. Chlorine is 35.45. What's potassium? It's on the periodic table. Okay, that's what it says. It said 39 point what? Oh, okay, we'll just say 0.1. So this was the Cl and this was the K. So that would be 5, oops. 5, 5. Before, carry the 1, 7. So there's our molar mass. We got 0.078 moles KCl. What goes on top? What goes on bottom? 74.55 grams on top, moles on bottom. So how many grams is that? Okay. And then this 5.8 is what we're going to plug in right up here. And we have 75 milliliter solution. So now percent is going to be equal to 5.8 grams. That's the KCl divided by 75 milliliters of solution times 100. Seven 7.7%?
Yeah.
Fine. I hope a problem like that would be just something you would crush on the exam. Okay. That's almost straight plug and chug into the equation, except for we use the molar mass to convert moles to grams first.
I feel like as long as we just remember these equations.
Yeah. B is the same way, so I'm gonna skip over that. All you do, calculate the molar mass of sucrose, convert moles to grams, plug it in and divide by the 380 milliliters times 100.
So like, what's like grams? You guys just have to keep that on the side for me at least.
Yeah.
Are there like, there's other practice problems, right?
Oh, yeah.
Okay.
I have a whole list of ones I recommend.
Can we do them in like class?
For sure, always. That's my dream, that you would do those things. I don't dream about it at night, but that's what I want you to do. Okay, so this one is straight asking about molarity. What is the molarity of the following solutions? So again, there's 3 here. I'll do an example of 1. Oh boy. I know, all my batteries are dying over here. That's what happens by the time you get to Friday. I'm like so done after my Tuesday, Wednesday, Thursday stint. And I'm like, I don't even care. I don't remember anything. Okay. So what is the molarity? So we got 12.5 grams NaHCO3. What is that? Nobody knows what NaHCO3 is?
Like it's molar mass.
No, just how do you say it?
Oh,
what is that?
Sodium hydrocarbonate.
Sodium bicarbonate.
Oh, sodium
Thank
bicarbonate.
you.
Okay, I know y'all said that in my head.
Uh-huh, uh-huh.
No, I did. I got it wrong too. I just got it.
All right, 12.5 grams sodium bicarb and 350 milliliters of solution. So what's the equation for molarity? We're trying to calculate molarity here.
M equals over, what's it, grams? What? Grams over moles? No.
That's molar mass.
Yes, you are.
That's molar mass. What is molarity? Moles over liters. Okay, so we're doing A here. So molarity equals moles of sodium bicarb over liters of solution. That's molarity. And we don't do the times 100 or anything. So what do I need to do first? Yep, here we got to convert grams to moles. So since we have the good old internet, what is molar mass of sodium? You had your phone. Too bad that's not allowed. Okay, so 84.007 gram per mole. So we are gonna take 12.5 grams, divide by 84.007 gram per 1 mole.
Oh my gosh.
How many moles is that? 0.15 moles. Okay. Yep, milliliters to liters. So molarity is going to equal 0.15 moles divided by, so we take that 350 divided by 1,000, convert to liters, it should be 0.35 liters. Okay. So what's our molarity? Okay. Oops. There you go. So B and C would be the exact same way. You just find the molar mass of those substances, convert to moles, convert the milliliters to liters and plug it in. Okay. So that's quite a bit with calculating concentration in percent and molarity. This is a good practice problem as well. A flask containing 450 milliliters of 0.5 molar H2SO4 was knocked to the floor. How many milliliters? And this is, I pulled it right from the textbook, but I modified it a little bit. That's why I typed it. I don't forget what number it is. How many milliliters of a 0.25 molar solution of sodium bicarbonate would you need to pour on the spill to neutralize all the acid? So the first thing we need to do,
We have 2 minutes. Wait, is that gonna be like in one, someone?
no, we need to write a chemical reaction for this. You're tempted to do dilution problems on this, but there's a chemical reaction here. We have to plug in a mole to mole ratio. So it says we got H2SO4. And it says to neutralize all the acid. That's what was spilled on the floor. So guess what? This is our acid. It's going to react with NaHCO3, sodium bicarbonate, which is going to neutralize it. So guess what? This is our base. So based on what you know, and this base, by the way, it's going to break up. It's aqueous, definitely aqueous. Both things are aqueous. gonna break up into Na plus and HCO3 minus, okay? That's what ionic compounds do in solution, right? They just break up into their ions, they dissociate. So, based on what you know acids and bases do, uh-huh.
You're like HSO4.
So if it's gonna donate a hydrogen, then yeah, we'll have HSO4 minus left over. Okay, from the acid. And where's that hydrogen gonna go? They gave up a hydrogen. Where's that hydrogen gonna go? H2SO3. You mean CO3?
Yeah.
Yeah, so this right here is gonna receive that hydrogen. And when it does, it's gonna make H2CO3. Okay, now you still have sodium floating around. And that sodium would probably see that ion right there and maybe interact with it, but it's all aqueous in solution. So if you wrote it like this, I wouldn't mind. Now in the book, it'll tell you that this decomposes immediately into H2O and CO2. But again, if you left it as carbonic acid, I wouldn't count you wrong, okay? But you can just see when it makes water, that's how it's neutralizing, okay? So how would we balance this? So I am, for just the purpose of balancing our sodiums and everything, I'm gonna write this as NaHSO4.
It doesn't need to be.
One sodium. Three hydrogens. Yeah, we're good. 1-to-1 mole ratio there. Okay. So now how do we start the problem?
Well, my instincts are telling me since we have to write this out, then I have to go.
Yeah, anytime you have a chemical reaction like this, you've got to have the molar ratio. So this problem is, oh, there it is, right there. Remember this thing? It's a 3-step problem. So you start with the volume of the solution. We were given a volume of solution. So 450 milliliters of H2SO4. Now what should we do? Exactly, Gracie. She said convert to liters so that you can use the molarity, which is the 0.5 of the H2SO4 to convert to moles of H2SO4. So 1,000 milliliters, 1 liter. Now we're going to use the molarity. Okay, so 0.5 mole. I'm going to zoom in on this for a second. That's the same as 0.5 moles of H2SO4 per 1 liter, right? Molarity is moles per liter. So, do what? So I've converted my volume of acid to liters, and now I want to use the molarity to convert to moles. So I'm going to say for every 1 liter, it's 0.5 moles. H2SO4. But it's asking me how many milliliters of a 0.25 molar solution of sodium bicarb would I need to pour on the spill to neutralize all the acid. So what do I do at this point? Again, that's why I encourage you, go back and look at this diagram. We started with the volume of H2SO4. Step 1 was we use the, once we have it in liters, we use the molarity of our H2SO4. as a conversion factor to convert to moles of H2SO4. And what does step 2 tell us we need to do? Yep, which is, yep, so for every 1 mole of H2SO4, it'll be 1 mole of NaHCO3. And this would definitely be an open response question. I would definitely be looking for this step right here, because the units have to cancel properly. So far, we've canceled milliliters, we've canceled liters. All right, what's the last step if you want to go back to this? Now that we have moles of our other thing, sodium bicarb in this case.
We're gonna use the molarity of the Na.
Yep. Which is 0.25. How do I write that in? It's moles of NaHCO3, and I want that to cancel, and it's per 1 liter. And it says how many milliliters, so the last step is I'm just gonna go ahead and convert that. For every 1 liter, it's 1,000 milliliters, okay? So without the milliliters to liters conversions, this right here is what we're saying is the 3-part problem. Okay, step 1, step 2, step 3. But it looks longer because you got to convert from milliliters to liters and then back to milliliters. So 450 divided by 1,000 times 0.5 times 1 divided by 0.25 times 1,000. Thanks for coming, Olivia. Of course, have a good Thanksgiving. Anybody got it? Did you get it? What is it? 100? 900. Boom. Okay, could y'all handle a problem like that on the exam? All right, is this, yeah, this is the last problem I had. This, we haven't, again, covered equivalence or we haven't covered equivalence or electrolytes. Okay.
Yes.
Tomorrow?
We
Saturday? What?
gotta study on it Saturday.
No, I'm going to get donuts with my family. All right, which of the following, I'm gonna plug this stuff in or it's about to die on me. Which of the following, well, hold on, let me see. What is the charge on my Apple Pencil? Okay, I'm at 70%. Which of the following solution has a higher osmolarity? Did you have one like this on your homework? Mm-hmm.
And I knew how to do it, but now I don't.
Okay, someone tell me what we need to do since y'all already did it. Yep. Is that what you said, Grace?
Of course.
So A here,
I always know.
0.25 M. And so we got KBR. How many particles do you get from that? 2. So times 2 equals 0.5 osmoles. Okay, then we've got 0.2 molar of Na2SO4. How many particles do we get from that? Yep, so times 3, 0.6 osmoles. So the 0.2, looks like I've circled both. The 0.2 of the sodium sulfate would have the higher osmolarity. Now the B is harder because it doesn't give you molarity of both. So leave NaOH there in molarity, but first we need to take 3% mass volume and convert that to molarity. How do we do that?
How do we?
And let me make sure that nobody's waiting in the hall to get it. They are? Then we gotta be there.
They got 6 minutes.
Oh, try 11. Okay. Yeah, we gotta be there.
They have 6 minutes. We're not wait 6 minutes. We are not done.
I have to shut everything down. Okay, real quick. Real quick. We gotta do this in 1 minute. Okay, so 3 mass volume percent equals grams of NaOH over milliliters of solution, right? Times 100. So the way this is hard because you just kind of have to assume a certain number, like 3%. If I had 100 milliliters, how many grams would that be equal to give me 3%? What is 3% of 100? 3. So this is hard because you actually have to, I probably wouldn't do this on the exam. Okay, so if that makes it easier, then we don't have to finish this, but you would, okay. You would assume 3 grams, you convert it to moles, divide it by 100 milliliters and whatever, you don't care. Okay, and then you would compare once you have it in molarity, okay?
Nice to know.
All right, thanks for coming.